Okay, so let's go ahead and focus a little bit more on those IMFs, or intermolecular forces we've been talking about, and seeing how they actually apply to the properties of the molecules we've been learning about. So again, for our IMFs, we have LDF, which is London dispersion forces. They are the weakest force overall. They are present in everything. They're only truly most important in nonpolar compounds because it's the only thing holding a nonpolar compound together, together, meaning with other nonpolar compounds. The compound itself is held together by covalent bonds, but holding multiple compounds together is done through LDFs for nonpolar compounds. We also have dipole-dipole, which is present in polar compounds. So to get a polar compound, you have to have a polar bond, and the molecular geometry has to allow the molecule to be polar as well. We also have hydrogen bonding, which is a very special case of dipole-dipole, a very strong dipole-dipole, specifically hydrogen bonded to oxygen, nitrogen, or fluorine. And it will then interact with a electronegative element such as oxygen, nitrogen, or fluorine on a different molecule. The hydrogen atom will. It's a very polarized bond, meaning that it's got a lot of electronegativity difference between the atoms. So the oxygen, nitrogen, or fluorine in that case will pull most electron density towards itself, not allowing for a lot for the hydrogen to have, making it very electropositive. Hence the word polarizing bond. We'll talk about polarity and polarizability in this unit as well. And then we have the ion dipole, which is how ionic compounds dissolve. So just looking at first here on the left-hand side are noble gases. If we look at the boiling points of our noble gases specifically, we see here helium through xenon. So not every noble gas, but the ones that are naturally observant around us. And we can see their relative size here, their molar mass, and their boiling point. Now, what I want you to realize is that, yes, as they get heavier, their boiling point is increasing, but it's not a direct comparison to molar mass. It's actually due to the size, which leads into the polarizability of the molecule. So don't pay attention so much to the molar mass. It's here to kind of emphasize the size difference. But what I want you to think about is the size of the atoms. And this leads into this idea of polarizability. Larger molecules, larger atoms, larger species, the larger it is means the more polarizable. Which is going to lead to a greater effect of the IMF. So all of our noble gases, the only way they're interacting with each other is by LDFs. They don't have anything else. They're just an atom. They have London dispersion forces. But as I go up in size, the size leads to more polarizability, which again, I will talk about in a second. I'm going to show you a video, try to describe it as well. Polarizability is how much can it distort that electron cloud? How much can the electrons in that species move or polarize from just an equal setting on the molecule? And if I look at my halogen phases, some of these you guys probably already know, hopefully already know, but it kind of explains this as well. If I ever forget, I can think about the phases on the table. I know that fluorine and chlorine are always going to be gases at room temperature, while bromine is a liquid at room temperature, and iodine is a solid at room temperature. And why is that happening? It's happening because of the polarizability of these molecules. F2 is the smallest. Fluorine is the smallest atom in this list. So F2 molecule will be the smallest molecule in this list. Iodine is the largest molecule in this list, which means I2 will be the largest molecule in this list. The larger the molecule, the more polarizable it is. These here are trying to show you the general sizes of these things. So this would represent like F2 versus Cl2, Br2, and I2, okay? So what is polarizability? It's kind of hard to visualize it, but once you get it, you got it, okay? So polarizability, LDFs, or your London dispersion forces, increase with larger, more polarizable electron clouds and surface area. Think about your electron cloud as an actual cloud, Picture a cloud in your mind. Clouds don't just keep their standard shape, right? We don't just have a cloud that always has, say, this shape. This cloud may move and be this shape. It may move again and be this shape. If we look at clouds in the sky, they're not always keeping the exact same shape the whole time. They're moving with the air in the atmosphere. Think about electron clouds the same way. The electron cloud is electron density. Basically, it's where can the electrons reside, okay? The larger these atoms are, the more these clouds can move, the more shapes they can take, the more surface area they can have. Polarizability, though, is the ease at which this electron cloud can be distorted. Large atoms and molecules are more easily polarized because they have a greater polarizability. They're more easily polarized than small atoms and molecules. Thus, London forces increase with molecular size. If I have a small cloud, it's a lot harder to distort than a big cloud. A big cloud is just easier to distort. Generally speaking, in the absence of other effects, substances containing large atoms and molecules will have higher melting points and boiling points compared to substances that are smaller in size. Dispersion forces, again, are present in all molecules, polar and nonpolar. They're present in everything. But, for example, place of diatomic halogens that are of increasing boiling point, F2 to Cl2 to Br2 to I2, would go just like that. F2 will have the lowest boiling point, followed by Cl2, followed by Br2, followed by I2. And that's because of the relative size of the molecules. Again, these circles on the side here are not actually drawn to scale, but they're trying to show you the polarizability of the molecules. Sorry. Of course, when I try to scribble it away, it doesn't work. F2 here is a pretty good circle. It's not very distorted or mishappen. This is definitely distorted because it's a lot larger. It's easier to move or it's easier to distort. That distortion, the ease at which that can be distorted, that electron cloud, is that concept of polarizability. So we're gonna watch this video really quick. I'm gonna link the video into here, and we're gonna watch this video on giant bubbles. What I want you to think about when you're watching this video is, when you're watching the bubble itself, the small bubbles don't distort. The large bubbles are much more just easy to distort. They have much more distortion to them. So these small bubbles are not very polarizable. They do not have a lot of distortion. The large bubbles are very polarizable. They distort easily. So that easier the distortion of that bubble, the more polarizable it is. I want you to look at the bubble and think about that, but in the relation to an electron cloud. Again, an electron cloud is the area of electron density, and it's where the electrons within the molecule can reside. So as you're watching this go through, watch those bubbles. That really big bubble that's going through, pretend that's an electron cloud. It's incredibly distorted by the air. As a small bubble goes through, it doesn't have much distortion. But that real small bubble compared to the bigger bubble. Watch the distortion of those clouds. Again, I know these are bubbles, but think about this in respect to an electron cloud. Again, electron cloud is a representation of electron density, which is where the electrons can reside within a molecule. How, again, the size of an atom, the size of a molecule is dictated by the electron cloud. It's the electrons that take up the bulk of the space of an atom or a molecule because your protons and neutrons are enclosed. So hopefully that video helps you make a little bit more sense of this idea of polarizability. But again, the smaller the molecule, the less polarizable it is. The less polarizable means the less distorted that electron cloud is, which means it doesn't have as large of a surface area. The larger the molecule, the more surface area it has. And what it is it's the surface area of one molecule that can interact with the surface area of another molecule. And it's these connection points between them. These connection points between them is the LDFs. The more connections they can have between them, the stronger the overall properties will be of the compound, meaning like the higher the boiling point, the higher the melting point. And that's why LDFs are really important. When we get heavy molecules, they can actually make a difference because the heavier it is tends to lead to bigger size, okay? It doesn't mean molar mass is it. It is the size. It actually is size that's dictating this, not mass. But in order to be a heavier mass, you tend to be a bigger molecule. So we see that trend, even though you are looking at size specifically here, okay? The bigger the atom, the bigger the molecule, the more distorted that electron cloud, the more overlap it can have between the molecules, leading to stronger forces. We've already talked about hydrogen bonding some, but let's review it again. A hydrogen bond exists when you have hydrogen covalently bonded to an oxygen, a nitrogen, or a fluorine atom. That hydrogen is very electropositive compared to the oxygen or nitrogen or fluorine that it's bonded to. So for example here, the oxygen is very negative, leaving that hydrogen very electropositive. It's a very polarized bond. What I mean by that is the oxygen is pulling all of the electron density towards itself, giving that hydrogen less than what it needed. And so when another oxygen is around from another water molecule, that hydrogen is very partial positive charge, the oxygen very partial negative charge. The hydrogen forms an electrostatic attraction to just stabilize itself. It's lost a lot of its electron density to the oxygen it's actually covalently bonded to, so it forms a hydrogen bond with another molecule. Now, in order to do this hydrogen bond, the hydrogen not only needs to be, again, covalently bonded to one of these things, but the bond that, or the molecule that it's hydrogen bonding to has to have a lone pair. We don't usually draw them in here, but it must have a lone pair on it as well. Again, hydrogen bond is a type of a dipole-dipole. It is a very strong dipole-dipole. It's a special case, but a very strong dipole-dipole. So substantial energy is required to overcome these hydrogen bonds. Because these substances hydrogen bond, and because it takes so much energy to break these apart, these compounds that hydrogen bond typically have higher than average melting and boiling points, which we see with water. They have higher delta H vaporization, delta H diffusion. Remember, delta H is just heat of reaction. So this means the heat to vaporize, which we will talk about in just a bit, but vaporization is going from your liquid phase to your gas phase. And the delta H diffusion is the heat to fuse or melt something. They also have higher viscosities, which we've already talked about. Viscosity is the resistance to flow. The stronger the IMF, the more resistance to the more resistance it will have to flow, because it's holding the molecules together better. Lower vapor pressures and lower volatilities as well. Again, vapor pressure, just the ability to escape into the vapor phase, and volatility, it's the ease at which it escapes at that vapor pressure. Without actually boiling, it's able to go into the vapor phase. So, such as water being spilt on the countertop and it not reaching its boiling point, but water still evaporates away. That means that it technically has a vapor pressure and it is volatile because it can escape without actually boiling away. So this is just a graph to show you really the effect of hydrogen bonding and how impactful it is on the properties of the molecule. When I look at this graph, what I see on my x-axis is the molar mass. But again, I want you to be careful thinking about molar mass. Molar mass leads to size as well. So although we often compare things by molar mass, polarizability is because of the size of the molecule, okay? And then the boiling point. if I look at group 6A elements here, I've got CH4, SiH4, GeH4, and SnH4. So carbon tetrahydride, silicon tetrahydride, germanium tetrahydride, and tin tetrahydride. Okay. I see as I go from carbon to silicon to germanium to tin, that's basically going across the table. So the molar mass is increasing with these molecules, meaning that they're going to be slightly bigger in size as well. Yes, the metals are decreasing in size a little bit, but the molecules themselves are getting a little bit heavier. I see that their boiling point is increasing. Okay, that makes sense. They're heavier. It's going to take a little bit more interaction among the molecules. So they're a little bit bigger molecule. They can have bigger size to it, bigger interaction, bigger surface area. Oh, that's fine. But then I look at the group 4A, which is oxygen's family. H2O versus H2S versus H2SE versus H2TE. And I see that the three of these follow the rules. These three follow the rules. But then water's way up here with a boiling point of 100 degrees Celsius. And the only difference between water and these others is that water is able to hydrogen bond. Notice this is the 0 here. These are well below 0, yet water's boiling at 100. Water has a very small molar mass. 18 grams per mole is incredibly small in the grand scheme of things. But it boils at 100 degrees Celsius. That's huge importance to our world from an ecological standpoint, from a human standpoint, etc. There's very strong benefits of the fact that water hydrogen bonds and has such a high melting point and such a high boiling point. But it's causing these properties to come through as well. So, why do I say hydrogen bonding is so important? These are just a few of the applications of hydrogen bonding that makes it so important. There's more. But first off, hydrogen bonding is responsible for the enormously high melting points of water, ammonia, and HF, which we'll talk about in just a minute. But if I think about water, 18 grams per mole, ammonia, nitrogen is 14, hydrogen's 1 AMU each, so about 17 grams per mole. HF, I believe fluorine is about 19 grams per mole, so HF would be about 20 grams per mole. They all have about the same molar mass, but they all melt and boil much higher temperatures than we would otherwise suspect, and it's due to hydrogen bonding. Why do I care though? Well, one of the reasons I care is because of hydrogen bonding, and we talked about this in a previous module, but because of hydrogen bonding, ice actually becomes less dense than water. And that's because of the way that the water molecule orients themselves, it actually forms a tetrahedral shape in the ice crystal to maximize its hydrogen bonding. In order to maximize that spacing, though, for hydrogen bonding, it leaves space in the crystal structure. That space is just literally that, it's empty air. It's space between the atoms. But that space makes ice less dense than water. Why is that so important, though? Well, I was born and raised in Minnesota, and ice fishing was a really important part of my family's culture. My grandfather loved to go ice fishing. Ice fishing may sound like, okay, cool, you went ice fishing, but here's the thing. Why was that important? It fed my family, yes, but even more than that, ice forms at the top of the water, which means when fresh water freezes, it's freezing top down, meaning that all the aquatic life is still surviving underneath that ice. That is quite important. If water froze bottom up, most species have their solid phase is more dense than their liquid phase, meaning that it would sink, right? If ice was more dense than water, then lakes would freeze bottom up and it would kill off our entire aquatic system in anywhere that was cold enough to freeze in the winter. And that would just be detrimental to the entirety of our ecosystem. Another important application is the DNA. The double helix of DNA is caused by hydrogen bonding. And so the ability of DNA to perfectly replicate itself is due to hydrogen bonding. It's such a simple concept, but it has such huge, important consequences to the way our lives actually work. So again, for molecules of similar size, which you can relate size to molar mass, okay? The strength increases as I go from dispersion forces to dipole-dipole to hydrogen bonding to ion dipole. Remember, dispersion or LDF are present in all molecules and atoms. Dipole-dipole are only present in polar molecules. Hydrogen bonding is for molecules containing hydrogen, and they are directly bonded to a fluorine, oxygen, or nitrogen. They will then hydrogen bond to a different molecule. It could be the same molecule, like same type of molecule, but a different molecule, of course. It could be the same type, such as water, one water molecule, hydrogen bond with another water molecule, or it could hydrogen bond with a different molecule. But the molecule it hydrogen bonds with, the oxygen, nitrogen, or fluorine that it attracts with on the other molecule must have a lone pair on it. The reason I emphasize that is because something like ammonia can hydrogen bond, but something like NH4 plus cannot. And if you think about the structure, the Lewis structure, ammonia has a lone pair. It can hydrogen bond. Ammonium does not have a lone pair. So the ammonium could hydrogen bond to the ammonia, but ammonium cannot hydrogen bond to itself because it doesn't have a nitrogen with a lone pair. Doesn't have a nitrogen with a lone pair to hydrogen bond to. And then ion dipole, again, that is how solutions are formed. That is how ionic compounds dissolve, but that is the strongest of them. It's a mixture of ionic compounds with polar compounds. Notice here the polar compounds part. So dispersion force can become very, very strong, meaning LDF here, can become very, very strong, and strong, as strong or even stronger than the others if the molecule is large enough. Let's look at some examples here. First up, we have CH3, CH2, CH3. Let's see, what I have drawn is not that, so let's just fix this. Let's match these up. This is CH3. What is that mass? That mass is correct. So let's just redraw it because I don't want to have to figure out the new properties here. So this one, ignore that. I apologize. Let's just redraw the actual correct structure. Someday I'll fix it, but most days I'll forget. There. So this is the structure here. First up, though, CH3, CH2, CH3 is just called propane. We have 3 carbon atoms and 3, 6, 8 hydrogen. And its molar mass is 44 grams per mole. We have a dipole moment of 0.08. Again, a dipole moment is the measure of the difference in electronegativity. So you can think about it like a measure of polarity. Of the molecule. Its boiling point is negative 42 degrees C, pretty low. Next up, I have what we call dimethyl ether. So C2H6O is its overall formula. Molar mass is 46, almost the same. But I have a pretty increased dipole moment, 1.3. And then again, D or mu is how we represent it. And I see the boiling point is basically half, negative 24 degrees C. And I can see the structure of it. This molecule is not incredibly polar. I realize that language isn't greatest, and I apologize. It's not very polar, but there is some polarity here. It is a sp3 hybridized oxygen. The carbons are also sp3 hybridized, and it is a overall polar molecule. It's just that these methyl groups on the side, these are called methyl groups. CH3 is a methyl group. These are big enough that they're starting to take up space for the oxygen, hence the low polarity to it. It is sp3 hybridized. All 3 central atoms, carbons and oxygens, are sp3 hybridized, which means they are tetrahedral, and it is a polar molecule. Okay, if I look at this molecule, this is an aldehyde functional group. So this is called ethanal. You guys will learn that soon enough. But the way it's connected, we can see formula C2H4O. Molar mass is 44. Dipole moment, 2.69. So we've definitely doubled the polarizability or the electronegativity of this molecule. Pretty polar right here because of this carbon-oxygen bond. Because again, carbons, hydrogens we assume are nonpolar, but the carbon-oxygen bond is a polar bond. It's also double bonded, which makes it a slight difference there. Boiling point is increased up to 20. If I look at this molecule right here, let's talk this out. We've got 3 areas of electron density right here. Change this so I can do a little smaller font. 3 areas of electron density. So it is sp2 hybridized. Trigonal planar structure. Okay. The carbon here, also sp2 hybridized, trigonal planar. Carbon atom right here, sp3, tetrahedral. Remember, this bond here is polar, and it's pulling it towards the oxygen. And last up, I have CH3CN, methylcyanide. I have a molar mass of 41, so it is the smallest, but my dipole moment here is 3.92. That is the largest dipole moment I see in this list, and the boiling point is up to 82. So definitely something happened here with that electronegativity, right? If I look at the molecules here, again, this carbon, the way this is actually connected, this carbon has 3 hydrogens attached to it. It's just like that. We just write it as CH3 to make our lives easier without having to draw it all out. So these are the three central atoms I have. This is sp3 hybridized, so it is tetrahedral, and is considered nonpolar. The carbon here has 2 areas of electron density, so it is sp hybridized, it is linear, and this bond is nonpolar. The nitrogen, also sp hybridized, but this triple bond is definitely polar. It is a polar bond, and the nitrogen is more electronegative than the other species, so it is pulling the molecule towards the nitrogen. And I see that effect on the boiling point as well. So thinking about these ideas that we've just talked about, which substance would you expect to have the higher boiling point, N2 or HCl? Again, the stronger the IMFs lead to things like higher boiling point, because we have to break apart those IMFs to get the molecules to actually boil. When something boils, it's going into the gas phase. So we are breaking apart all interaction between the different molecules. We have to put in enough heat to get all of those IMFs to break apart. If I have N2 and I drew out the structure of N2, it just looks like this. HCl just looks like this. So how am I going to decide this? I'm going to think about what IMFs these things have. This LDF, everything has an LDF. But then that's it for nitrogen. It doesn't have anything else. It just has LDFs. Whereas HCl is also a polar bond and a polar molecule. So it has dipole-dipole. Hence, the higher boiling point here will be this molecule. What is the predominant IMF in each of the following? Predominant means which one is strongest? And sometimes it's easier to draw them out. Sometimes you can see them right away. Do what you need to do. But for this, I'm going to go ahead and draw them out so we can all see them together. If I look at CO2, I get this general structure. Now, yes, these are polar bonds. But remember, we've talked about CO2. They're polar bonds, but they're canceling each other out. This molecule is completely symmetrical. Because it is symmetrical, it is nonpolar. And therefore will only have LDF. If I look at ethanol, CH3CH2OH is ethanol. CH3, this means these 3 hydrogens are attached to this carbon. Carbon has to have 4 bonds, so it must be bonded to the next carbon. CH2 means these 2 hydrogens attached to this carbon. And then the O and the H, again, H means it's attached to this O, so the O must be attached to the carbon. When I look at this, I know it has LDFs because everything does. But then I say, are there any polar bonds? And I'm like, oh yeah, there's polar bonds here. And I say, is the molecule polar? And I say, let's look at it. Let's think about this. These are all sp3 hybridized, which means they're all tetrahedral. That oxygen is making the overall molecule not symmetrical. It's pulling electron density towards the oxygen. But the tetrahedral shape, remember oxygen is, tetrahedral electron geometry, tetrahedral molecular for the two carbons. The oxygen is bent. So it's forming this kind of thing to its other compounds. It is definitely polar, okay? So I know I have dipole-dipole, but am I done? I need to think about hydrogen bonding. Right here, I have the ability to hydrogen bond. Hydrogen bonding is stronger than a dipole-dipole. It is a type of dipole-dipole, but it's so strong compared to a regular dipole-dipole that we pull it out on its own. And we say, okay, it has H bonds. Let's talk about the next one, SCl2. And I'm going to erase this because I want room. Let's talk about SCl2. I don't remember what the structure is of SCl2, to be honest with you. So let's see. 2 chlorines is 14 valence electrons. 1 sulfur is 6. So 20 valence electrons. Attach my chlorines. Okay. So it's bent. Because again, this is sp3 hybridized. Tetrahedral electron geometry, which means bent for its bent for its molecular geometry. Chlorine is more electronegative than sulfur. So it's pulling the dipoles, overall pulling it in one direction. It is a polar molecule, so dipole-dipole. And last is MgCl2, which is, by electronegativity difference, actually very, very polar, but we can treat it as on a compound as well. And when we see this little AQ here, this means it's dissolved in water, right? If I dissolve magnesium chloride in water, what happens? I form magnesium ions, and I form chloride ions. This is ion dipole. So an overall summary of the intermolecular attractive forces. Again, the top question, I really just need to move because I keep forgetting it's there, but which one is higher? Boiling point N2 or HCl? HCl because it is polar, while N2 is nonpolar. The same thing would be said if it was melting. HCl would be higher melting point than N2. Thinking about all of these things, everything else being equal, which IMF is the strongest? My ion dipole. Everything else being equal, which everything else means it has an equal size. Everything else being equal, which attractive force is the weakest? Your LDF is the weakest. What type of intermolecular forces are present in the following molecules? Methanol, CH3OH. If I actually drew that out, I've got carbon. The carbon is sp3 hybridized, which means it is a tetrahedral shape. Bonded to an oxygen. That oxygen is also sp3 hybridized, so tetrahedral electron geometry, but we see that it actually has a bent structure with its 2 lone pairs. Not only that methanol, we've got that perfect little combination there, which means we get our hydrogen bonding. If I look at sulfur dioxide, it's very similar to water in structure. Sulfur dioxide, let's see, 18 valence electrons. when I look at the sulfur in the center, what is the hybridization here? Oops. Sorry, trying to put my lone pairs. But hitting the wrong buttons on my iPad. So what is the hybridization here? It only has 3 areas of electron density, so it is sp2 hybridized, trigonal planar for its electron geometry. But when I actually draw that out, because of that lone pair, I have that bent structure. Now, it's not the same bent as water. Water has 109.5 base angle, so it's less than 109.5. This is a 120 base angle, so it's less than 120 because it's the lone pair. But overall, it's still polar. Oxygen is more electronegative than sulfur, so it has a net pull on the molecule, but they're not hydrogen bonding. Dipole. I'm just going to make this box bigger because I need it. Okay, phosphorus trichloride. What is phosphorus trichloride? Phosphorus is P, tri means 3, and chloride means Cl. So PCl3. If I drew out its structure, Lewis structure looks like this. I have 4 areas of electron density, which means the phosphorus here, sp3 hybridized, tetrahedral, electron geometry, but the molecular geometry is trigonal, pyramidal. The chlorines are all more electronegative than the phosphorus, so there is a net pull on the molecule, meaning it's a polar molecule. There's no hydrogen bonds, so it is dipole. If I look at potassium chloride, again, potassium chloride, KCl, but it does say aqueous. When I put this into water, I get Cl plus or K plus and Cl minus. So K plus Cl minus are ions in solution. This is ion dipole. Now, hexane. Hexane is an organic molecule. Hex means 6. Ane means all single bonds between the carbon atoms. So I have carbons. I have 6 of them in a row. And then I give all of them enough hydrogens to give them their formal charge of 0. When I look at that, every carbon here, every single carbon, 2, 3, 4, 5, 6, they are all sp3 hybridized. They all have electron and molecular geometry of tetrahedral. They are all nonpolar because it's a carbon-hydrogen bond, and the electronegativity difference there is nonpolar. It's 0.4 for its difference, so it will be a nonpolar molecule because it has nonpolar bonds. If you don't have polar bonds, you can't have a polar molecule. So LDF is the strongest it has. Now, dihydrogen sulfide. Dihydrogen means 2 hydrogens. Sulfide means sulfur, H2S. This is very similar to water. I'm going to draw this over here. That sulfur in the center, if I drew it out Lewis structure, I would draw this. If I drew out, I see that sulfur is sp3 hybridized. Electron geometry is tetrahedral. If I actually drew it out Lewis structure, or by Vesper, it would look like this. So it's a bent shape. Sulfur is more electronegative than hydrogen. It also has lone pairs on it, meaning it's not symmetrical. So there is no hydrogen bonding here, though. Sulfur is not one of the ones that we learn. It's not one of the rules. It's not electronegative enough to form that hydrogen bond. So here we are back with a dipole. Shrink that back down. Hope that makes sense.